So good morning, everyone. It's 9:30, so we are gonna start. So today, for the training of the project Ways to Biocomp, we will have a lecture just to make a little bit of context of what this is. This is a project that one of the activities, a European project that one of the activities is the training that aims to develop training materials and a skilled workforce for biomaterial-based manufacturing in the value chains of textiles, footwear, and packaging. So these different activities have also the different partners, but this series that we will present today are part of the CTEV's training activities. So who is CTEV, or what is CTEV? CTEV is the Textile Technological Center of Portugal. So we are located in Vila Nova de Famalicão, and we have services around the textiles. So testing, product and process certification, research, technology development and engineering, sustainability. So a lot of services related with also market-oriented textile areas. So fashion, sports, mobility, architecture, also mobility. And today we are going to focus a lot on mobility. And for today, we are also going to present these two projects that are connected in CTEV, because the CTEV are the leader of these two projects. And today, Ways to Biocomp brings also BEAT project. So BEAT project is the project of bioeconomy and textiles. And today we have a bit of what this project is. This project has 56 partners and 58 projects within this. So today we are just going to bring a bit with biocomposites, and just to make a little bit of context on what BEAT is. It's a bunch of areas, but basically what is circularity, what is new biomaterials to bring alternatives to fossil fuels, and what is the new metrics, what is the new eco-design, eco-engineering strategies for the textile sector. So these four pillars are the pillars of BEAT project. We focus on biomaterials, as I said, circularity, sustainability, and for the first time for this research center, we focus also in society, because we know that society needs to be part and collaborate with what is sustainability, what is the future. So bring together also how to partnership with the consumer and bring also the inputs of these ideas. So for today, the CTEV's developments in biocomposites are incorporated in the biomaterials pillar. So today we will bring a little bit of what textile-based biocomposites are, and we will present what is the relationship as well, what brings BEAT project to Ways to Biocomp. And today we have for our lecture Cristina Oliveira, Isabel Moura, Rita Marques, and Fernando Oliveira from CTEV that will bring you this news about biocomposites. So, Cristina, the floor is yours, and I hope you enjoy.
Okay, thank you, Raquel. Thank you. Just a minute. You already see my presentation, Raquel? Yeah?
Yes, we see.
Yeah, okay. Hi, good morning, everyone. My name is Cristina Oliveira, and I am from CITEV. I am the manager of mobility here at CITEV. The title of my lecture is Driving Sustainability in Textile-based Composites Using Different Approaches, 3D Printing using natural fibers, bio-based commingling yarns, bioprepregs, and among others. I will begin with an introduction to biocomposites and their application in the automotive sector. Later, I will provide a brief overview of other topics with focus on BIT project, which my colleagues will present with more detail regarding the goals and results in this project. So, to start, textile bio-based composites. So to begin and to start, I will show you a short video that provides a general overview of biocomposites. This video is in Portuguese. I apologize for that. However, the subtitles are in English. It was created as a part of the BIT project to promote the potential of this type of materials in Portuguese textile companies. Portugal has a significant expertise in textiles, and we believe that textile-based biocomposites materials could be a viable strategy for textiles and automotive companies and among others companies. So let's start to the video. As shown in video, the composition of biocomposites is based on a combination of at least two types of materials. A natural fiber reinforcement provides strength and stiffness to biocomposites, and the combination with polymeric matrix that acts as a binder, holding the fibers together and transferring loads between them. And then we can develop the biocomposite with the combination of these two types of materials. So you can call the biocomposites in different ways, green or fully bio-based, when all elements from renewable resources, and partially eco-friendly when we have a man-made of synthetic fibers with a combination with biopolymeric matrix and natural fibers plus petroleum derivative non-biodegradable matrix. So when you look at the biocomposites market, it is expected to grow at a rate about 17%, around 17% from the 2023 to 2027. Factors driving market growth include escalating demand for eco-friendly materials, coupled with a growing requirements for end-use sectors such as automotive, building, construction, and consumer goods industries, fostering business opportunities and revenue growth. It is expected in the growing demand for the biodegradable and renewable materials, which biocomposites are viable alternative to the traditional plastics. Furthermore, government policies aimed at reducing carbon emissions and promoting biodegradable alternatives are also propelling the market forward. Innovations in production technologies are also enhancing a feasibility and a cost effectiveness of biocomposites, making them an increasingly attractive option for several industries. So we identified 5 main advantages and 4 main limitations for the biocomposites. The 5 main advantages are the low density, the renewability, the biodegradability, the low cost, and the low abrasiveness. For the limitations, moisture sensitivity, thermal sensitivity, variability in properties, and lower durability. Of course, when we are talking about the natural materials, the durability is a big challenge for us, for the researchers to provide solutions that the durability, for instance, for the light fastness could be a huge problem for us in our developments. I'm sorry. Next. While biocomposites have many advantages, their mechanical properties can be inferior to those traditional composites. Enhancing these properties through the surface treatments, for instance, and hybridization with the synthetic fibers is an area of ongoing research. It is also important to develop the properties of the natural fibers used as a reinforcement improvement capability between the reinforcement and the matrix by taking account, for instance, enhancing the biocomposites recyclability and reducing the flammability. Here you can see several applications for the biocomposites for technical applications, for instance, automotive, construction, aeronautic, aerospace, defense, sports, and medical. When you think in automotive applications, we identify 5 main drivers forces: the new vehicle types, connectivity, comfort, sustainability, and cost efficiency. When you look for the sustainability, of course, you are thinking in application of eco-friendly materials and lightweight materials, thinking in automotive applications. When you are looking for the automotive textiles, we know that automotive textiles contains about 40 square meters of textiles materials used in car interior trims, which includes different type of components. For instance, airbags, headliners, carpets, side panels, and covers, and also reinforcements, of course. The current trends such as zero emissions vehicles and carbon neutral manufacturing demonstrate a growing significance of sustainability in automotive industry. The weight reduction via employing biocomposites supports the objective of the European Association of Car Manufacturers and the European Commission to reduce the carbon dioxide emissions. So in this slide, you can see several applications that automotive sector has applied with biocomposites. Thinking or looking for big project. In big projects, we are developing different technological approaches for developing textile intermediate solutions for biocomposites, the biocoating 3D, hybrid yarns, bioprepregs, bioformulations, and bio-CMCs. But what are the textile intermediate solutions for biocomposites? The textile intermediate solutions are ready-made materials which comprise textile reinforcement form and a polymer matrix. It's a composite material made from pre-impregnated fibers with a polymer matrix. Why bio-based? Of course, bio-based because the renewable sourcing, biodegradability, recyclability when you are thinking about natural thermoplastic prepregs, for instance, customizable, low carbon footprint, and natural aesthetics. And why thermoplastic? Recyclability, materials with using thermoplastic matrix could be recyclable, supporting the circular economy, all-in-one integration, facilitating the processing, durability, resistance to the impact, wear, and corrosion, stability, doesn't need refrigeration or freezing, and high producibility, easily thermomolded for the efficient high-value production, ensuring the rapid or the fast manufacturing. So, thinking in the 5 main technological processes that I identified before, biocoating 3D have the main goal to develop a yarn pre-impregnation through the coating and subsequent additive manufacture of biocomposites. Here, my colleague Isabel Moura will present to you with more detail all the goals and objectives, goals and results for this project, for this technical approach. Hybrid yarns, Fernando Oliveira will present to you all the detailed information about this topic, about this technological approach. The main goal of the hybrid yarns is the development of new natural-based hybrid yarns, commingling yarns featuring homogeneous distribution of reinforcement fibers in the matrix and improved performance. Bioprepregs, we have here written marks to show you all the information, all the goals, also on the results of the BIT project. But I will I will do a short overview. What is the bioformulations? The main goal of the bioformulations is the combination of biopolymeric matrix with natural based waste fibers and leaves. Basically, you have a mix of fiber residues with a biocontact polymer in order to obtain a bioformulation with application in automotive industry. Here you can see some of our results. We are doing a lot of work and we are using a lot of wastes and fibers in order to have this type of bioformulations. BioCMCs is a novel approach for the sheet molding compound using a renewable or biological materials. The main goal is the replacement of synthetic fibers and fossil-based thermosetting polymers. We are mixing, for instance, natural fibers with biothermoplastic matrix. And here you can see all the results that you are obtained at the moment. AMP, for instance, with polyamide 11, lyocell with polyamide 11, and other type of combinations in order to develop the biosynthesis. So thank you for your attention and enjoy the following presentations. Please feel free to contact Jeff here, my contact. For questions, discussions, please feel free. The next is Isabel Mora.
Isabel, you are without microphone, so. We are seeing your notes. We are seeing it now.
Raquel, it's okay?
Yes.
Yeah, okay.
Thank you, Isabel.
I can't hear you. Could you
We are able
repeat,
to
please?
see. We are able to see everything okay. Yes.
Sorry, now I'm going to share my presentations. As previously mentioned, in the current presentation, I'm going to talk about the technological approach for the development of intermediate textile solutions for biocomposites applications. In particular, 3D printing using natural fibers as an emerging technology in sustainable manufacturing. So first of all, a brief introduction to the 3D printing technology. This technology, I'm sorry, there's an issue with my presentation, I'm sorry. Okay, this technology uses materials that are dispensed from a nozzle onto moving platforms. With this technology, it is possible to produce layers of patterns, resulting in 3D objects. And also with the 3D printing, it is possible to control not only the amount of material, the rotation of the platform, but also the design of the objects that are controlled via graphic design software. Moreover, the objects can be constructed by following a computer design, a layer on top layer. This is the basic principles of 3D printing. Now some topics regarding the evolution of 3D printing. In 1984, this technology was developed. 2 years later, 3D printing was patented. And later in 2005, the first high-definition color printed was released into the market. More recently, in 2020, a bioprinting of functional human limbs and organs was carried out, and is expected that in the near future, in 2025, a global network of industrial scale 3D manufacturing centers, including several areas like clothing, electronics, life goods, etc. Some advantages and also some drawbacks regarding 3D printing. Regarding the advantages is a rapid prototyping, allows to produce complex shapes, is easy to use. It means that no skilled person is needed, reduce the design complexity, and is also cheaper than any other processes. Regarding the disadvantages is a slow process. Most of the times the components do not have enough strength or mechanical properties. Also the cost of raw materials that are quite expensive, and there is a limited material selection and variety. Is also a misused technology. In this slide are mirrored some of the 3D printing applications, for instance, aerospace, architecture, automotive industry, consumer goods, consumer electronics, defense industry, education, medical industry, and also mold industry. Concerning the 3D printing materials that are currently used, they are mostly derived from non-renewable sources, like ABS, polylactic acid, polyvinyl alcohol, polycarbonate, and soft polylactic acid. But the goal is to replace these current materials by the so-called emerging biomaterials, including natural fibers such as hemp, flax, wood, bamboo, cotton, etc., and also some sustainable polymeric filaments. Here I show you a brief state of the art regarding the use of continuous natural fibers combined with 3D printing technology. So the authors found that the properties of the binomial flex fiber and the polylactic acid has a polymeric matrix. They found out that the natural fiber field composites using PLA as the matrix was found to be weaker in terms of mechanical properties when compared to the thermocompressed composites. So they state that this is a biggest challenge in the field of the 3D printing of natural fiber biocomposites that can break away from conventional material design practices and can be achieved through multidisciplinary collaboration between biomimicry, material science, and other technologies. Other findings report that also the combination of cellulose has a versatile renewable feedstock and the design freedom offered by additive manufacturing, 3D printing, creates an ideal synergy for developing sustainable solutions for advanced applications, and in this case, in particular, in biocomposites. So the future of green composites lies in the innovative use of green raw materials, industrial waste, and also the use of recyclable materials. Nonetheless, it is essential to have some considerations regarding the use of natural fibers, because most of these materials cannot be used as they are present in nature, requiring additional processing. It is critical to choose the appropriate materials based on the desired part specifications. For instance, their stiffness, strength, the chemical bond with the polymer matrix, and so on. Also, it is important to choose an effective cleaning method. The most common is water treatment that have been shown to remove all the residues or most of the residues, and in this way can improve the adhesion between the polymeric matrix and the fibers. In a similar way, the right choice of the sustainable polymeric filaments is also essential, namely in terms of recyclability and biodegradability. Materials such as polyethylene terephthalates, polylactic acid, tire-polyethylene, and thermoplastic urethane can be recycled. In a similar way, materials such as polylactic acid, nylon, ABS, and polyethylene glycol are bio-based and biodegradable materials. And this type of polymeric materials should be the most adapted to its sustainability. Regarding the 3D printing technologies for the development of continuous fibers, they are designated according to the methodology or the way how the matrix and the fiber are joined together into the print nozzle and deposit. So we have different technologies: in situ impregnation, co-extrusion with top-preg extrusion, in situ consolidation, and inline impregnation. So we have the pilot line implemented at CITEV since 2023 for 3D printing based on co-extrusion with top-preg approach. Using this approach, the selection of the materials, it means yarns, fibers, and also polymeric filaments with the right properties is critical, namely the diameter, the melting points, the compatibility between the fibers and polymers, in order to obtain 3D structures, 3D textile structures for biocomposite applications with excellent properties. For application in mobility and the clothing accessories in these particular projects. So as stated before, the combination of sustainable polymers and natural fibers with good interface bonding and appropriate eco-design allows the development of sustainable materials that serves as the basis to create new structures for 3D biocomposites. That includes defense, biomedical, food industry, architecture and construction, energy, automotive industry, fashion, and footwear industry. But the biggest challenge in the 3D printing using natural fibers is, without any doubt, the need for specialized equipment and also the optimization of printing parameters in order to achieve the desired materials with good print quality. Here I show you some results, some ongoing results regarding the natural yarns coated with different thermoplastic polymers, such as polylactic acid, PHA, and polyethylene glycol, or even polyamide, and also a proof of concept resulting from the combination of a smooth polyamide and also a cotton yarn. In a similar way, here we have also two proof of concepts. On the left side, a PHA layer with cotton yarn on the surface, and on the right side, a PHA structure with cotton yarn reinforcements, composed by several layers. And a PHA structure with several layers of cotton yarn inside, integrated into a component. Also, I have here to show you more two proof of concepts that result from the combination of polyethylene glycol as a polymeric matrix and flex yarn or lyocell yarn. Nonetheless, there are several changes that need to be taken account to fully harness the potential of continuous filaments-based natural fiber composites, namely the proper material selection, controlling the morphology and thermal properties to ensure the filament is printable and results in good printing quality. Also, the optimization of printing parameters, namely the build orientation, fill percentage, and layer width, that can improve the mechanical performance of the printed parts. The structural investigation, there is a lack in terms of information regarding the study of mechanical properties, interface adhesion, and thermal properties to enhance the printing ratio and fabricate 3D printing materials with controlled structural features, and is critical to customize and have a design flexibility for industrial applications requiring covering material science processes, equipment, structural design, biomimicry, and so on. So if you have some questions, comments, please feel free to contact me. Thank you for your attention.
Hi, everyone. Are you listening to me? I hope so. Yes. So I will share my presentation to you about hybrid yarns or commingled yarns, natural and bio-based commingled yarns as intermediate solutions for composite materials. We'll start this, sorry, just a little bit. Start this presentation by having some definition on the concept, showing different types of hybrid yarns to you, checking the possible natural and bio-based solutions that are available, advantages and drawbacks of this type of solutions, and then check some technologies that we can use to produce these hybrid yarns, and then check some application and some results that we are achieving here at CTEV. Okay, a commingled yarn or a hybrid yarn is a hybrid structure in which we have two different materials in the form of fibers or yarns that are mixed to form continuous yarns. We'll see ahead of this in this presentation better explanations about this concept. But however, you can check here the scheme in which we have a set of reinforcement fibers and a set of polymeric matrix fibers that are joined together and blended together to achieve an homogeneous distribution of the fibers in the resulting yarn. And this, when I say homogeneous, in this case is homogeneous, it may not be, we'll see ahead. So in the pure commingling process, as a basic notion of a commingling process, there's some confusion between commingling and hybrid yarn. When we talk about the commingling process, we have two sets of multi-filament yarns that are blended together inside a commingling nozzle by the action of a projected airflow that promotes the mixture of the filaments of both yarns and promote an homogeneous mixture of the filaments in the resulting yarn. We'll see here the process. So we have two sets of yarns. They go through some mechanism, and they are joined in a commingling box in which that will have pressurized air flowing inside of them. There are lots of parameters to control in this process, such as tension of yarns, the title of yarns, the angle in which the pressurized air is inserted in the commingling box. It's a complicated process in order to achieve the most homogeneous mixture possible. In terms of this process that you saw in the previous slide, this is what is used in the market for the production of commingling materials, which is mostly what are mostly available are high performance materials such as carbon and glass and aramide mixed with synthetic fibers. There is one bio-based solution by Comfil as a PLA-based commingling solution, but mostly this is the commingling yarns that we can find in the market. As I said before, we can talk about commingling, and in literature we can find the term commingling to refer to multiple kinds of hybrid yarns, such as the ones that are shown in this image here below in the left side. Also in the literature, if we may have a textile structure in which we put natural yarns in the weft and synthetic yarns in the warp. We sometimes this is referred as a comminglet structure, hybrid structure, comminglet structure. Even if we use produce nonwovens that are based on synthetic and natural materials, they can be called commingling structures, etc. So there is commingling can be a term that is very widely used for a wide variety of concepts. And in these literature works, what we find when we talk about natural and bio-based solution is the junction of natural fibers and the bio-based polymeric fibers that we can see here. The most common are flax, hemp, jute, and the bio-based polymers that are here. There are other options. The blending methods, as I said before, there is a wide variety of blending methods that can be used to achieve comminglet structures. And what the technical aspects that are studied in this in the specific works that we found in literature are mostly related to studies of surface treatments, mostly surface treatments of natural fibers in order to promote a good adhesion to the polymeric matrix. Effects of the parameters in the quality of the resulting yarn. For instance, in the commingling process, checking the effect of the pressure of the air that is blown into the commingling box. In spinning or twisting, we can check the effect of the number of twists per meter, etc. And then also of course with the resulting yarns that these works are achieving, they produce further components and composites that are then characterized in terms of mechanical processes, etc. There are here in the next slide a few works that talk about this, as we can see here. Most of the materials that was shown in the previous slide are mentioned here, and also, as I said before, there are here developments of yarns, of hybrid structures, several kinds of structures. So in terms of advantages and disadvantages of this kind of solution, hybrid yarns, they are great for to optimize fiber and matrix compatibility. They can be tailored in terms of, for instance, percentage of weight of each fiber to achieve better results for a certain application. They are good for high complexity shapes or 3D geometries with complex shapes. The process of producing a composite is easier, is cheaper, and of course there is the question of sustainability, which in comparison with for instance the high performance materials like carbon that we spoke before, is way better. In terms of drawbacks of this kind of solutions, we can have processing difficulties in blending staple fibers and continuous multifilament fibers because they are materials of different natures. Also, the variability that can occur in natural fibers can be a complex thing to control in the process. There are thermal limitations for processing natural fiber-based composites, as I think it was already spoken before. The natural fibers also have questions regarding moisture absorption, and of course, when compared to high-performance materials, the mechanical properties are poor. But still, they are a valid option for a wide range of applications. So we'll run now into a more technical section of this presentation, in which I will explain very briefly the concept between some types of commingled yarns or hybrid yarns that we can produce. And most of them we can produce it here at CITEV as part of our work in the BEAT project. So for the commingling, we already discussed this. I'm not going to further explain the method. The resulting yarn will be something like this. This is a mixture of carbon and polyamide, but we can have this process applied to a natural and bio-based solution, for instance, using cellulosic regenerated cellulose materials in the form of continuous filament. Combined with some synthetic bio-based polymer to achieve some solution such as this one. Following to assembled yarns. This process is very straightforward. Is purely the joining of two or more distinct yarns into one single yarn without applying twist. Or I mean, we just join the yarns and they are parallel to each other in the structure of the resulting yarn. So for twisted yarns, we have a similar process to the one presented before, except when we join the yarns, we applied some twist to two or more plies of the yarn, and we achieve a yarn with that is more dense, and then we should control carefully the twist applied to these yarns, because it may influence then the production of fabrics, of knitting structures, etc. And also, as in the previous one, these yarns will be used for the production of textile structures, so they should be able to go into a weaving machine and produce a fabric. So when we produce these kinds of yarn, we should also take that into account. Moving on to the next one, we'll talk now about the spun yarns, which I will explain in more detail. The process is this, and there are several sequencing steps in this process, because we have to take two in this yarn. As we are making a hybrid yarn, we take natural fibers and bio-based polymeric fibers, and we have to mix them to obtain a resulting yarn such as this one with this internal structure. So I will explain a little bit of these steps. So we have the fiber mixture, we have the carding step in which we obtain a carded sliver. We have a drawing step in which each of these processes have the main objective of elongating the fibers, putting them parallel to each other. So when we get to the spinning process, we can actually spin a yarn, obtain a yarn from these rovings that we produce in the previous steps. So this is a machine that we have here at CITEV that is actually producing a hybrid yarn of hemp and polyamide. So a coarse spun yarn is basically the exact same process as I explained it before, except that we'll have a core yarn in which the spinning fibers will be spun around this core yarn. So basically, the structure of the final yarn will be something similar like this, in which this micrograph we can see various several yarns, this cross section of several yarns. So the process, the only difference in the process from spinning to core spinning is that in the core spinning we have a core yarn that is inserted in the final stage of the spinning process. So there are very similar processes, and they can produce different yarns. So another technique that we can use is related to a wrap spinning process that can produce a core of parallel yarns wrapped together by a warp thread. I'll show you here an image of a commercial solution of a yarn that is produced by this technology, and some yarns that we produce in the BEAT project. Then as applications of these yarns, we should take into account that these hybrid yarns represent intermediate solutions for application in composite materials. So with them, we can make fabrics, woven fabrics, knitted fabrics, unidirectional structures, any textile structures that can be processed in textile equipments. With these structures, we can further make some composites, and my colleague Rita will explain this better in the next presentation. So the yarns can be used to make textile structures that can then be used to produce components, solid components for a wide range of applications. So a little bit of for a final remarks, a little bit of the work we are developing here. So we are working with raw materials from hemp and BSL mostly as natural fibers. For biopolymeric fibers, we are using a wider range of synthetic biopolymeric fibers such as PA or PLA. Sorry. And for yarns, we have the same material. So into we get these hybrid yarns, as I showed before. We have spun yarns, cross-spun yarns, assembled yarns, twisted yarns, wrapped yarns that we use then to make structures, make fabrics that we can further test in a hot pressing machine to achieve something similar to a composite or a prepreg. With these materials, we perform some preliminary studies of the cross-section analysis in order to evaluate the impregnation of the polymeric matrix in the textile structure. We can do flammability tests. We can check mechanical properties, anything that can be related to the final application and it may be interesting to study. And then we, of course, can produce the woven fabrics, the knitted fabrics, and the UD structures that will act as prepreg materials to the producing stage of the composite parts. So, just a final remark that if you want to know more about this subject, we have a recently published paper on this topic. Was released about 3 weeks ago, and if you want to know more, it's a great way to do that. Okay, so check that, and of course, if you want to contact with some questions, feel free. Thank you.
Are you seeing it okay?
Yes. Just put in the presentation mode, please.
It's not in presentation mode?
Not yet.
Oh, sorry. Now you can see in the presentation mode?
But in the notes view.
Okay. Okay. Now it's all right?
No. Just try to share again.
Wait, sorry. Now I'm sorry. I'm sharing you. Okay. Can you see it?
When you put presentation, we just see the PowerPoint, like the full PowerPoint.
Okay, I'll try another way. It's loading.
Yes.
Okay, now you can see
Now
it.
we see, yes.
Okay, perfect. So my name is Rita, and I'm going to present you an overview regarding bioprepregs and fully bio-based composites. So what is a prepreg? Prepreg is an intermediate structure used for composites resulting from the pre-impregnation of textile structures using resin pastes, films, among other materials. So this intermediate structure is composed by two key components: the reinforcement structures, normally made of synthetic fibers such as carbon, aramide, and glass fiber, and a polymeric matrix that is impregnated into this reinforcement structure through different impregnation processes to form a prepreg. The primary textile structures used for prepregs include woven fabrics, knitted fabrics, and also non-woven fabrics. Additionally, they can also be used advanced textile structures such as unidirectional structures and non-cream fabrics. Regarding the polymeric matrix, for composites, they can be used different type of matrices, namely metallic ones, ceramic, and polymeric. But here in the prepreg, I'm just going to talk about polymeric matrices, and the most used polymer is epoxy resin, which is a thermoset. And regarding the thermoplastic polymers, the most used in the literature and commercially is polypropylene polymer and also polyamide. Due to the inherent recyclability of thermoplastic polymers, in my presentation, I'm just going to talk about the processes that can be applied to this type of polymers. So, how can you shift from a prepreg to a bioprepreg? Well, you first have to change the reinforcement structures, shifting from synthetic fibers to natural fibers, namely flax or hemp. And also we can use man-made cellulosic fibers such as lyocell and viscose. These reinforcement structures will be impregnated with biopolymeric matrices, substituting the fossil-based polymers by biopolymers. These biopolymers can be polyamide 11, PHAs or PHPs, and also polypropylene with bio content. Through the impregnation processes and combination of reinforcement structures and biopolymeric matrices, you obtain a bioprepreg. Here we have an overview of the bioprepreg development that starts with a biopolymer and a natural or cellulose-based reinforcement structure, and we can have different pre-impregnation methods. These pre-impregnation methods can be divided according to the state of the polymer, which can be a resin or a liquid polymer or a solid polymer. Okay. Now I'm going to talk you a little bit about the processes that use the polymer as in solid state, namely hot melt, in which the polymer is in pellet form and is extruded directly into the textile substrate. In the video, you can see the hot melt process, but for film production. However, this process can be done directly into the textile substrate. Regarding scattering, in scattering, the polymer is in powdered form, and this powder is scattered over the textile substrate that then is submitted to heat, which make the polymer melt in the textile structure, forming the prepreg. Layer alternation consists in putting polymer films over and above a textile reinforcement structure. And then this multi-layer structure is submitted to a process that combines heat and pressure to form a prepreg structure. The polymer can be also in fiber form, as already presented by Fernando. In this case, we can have biopolymeric fibers mixed with natural fibers to produce a hybrid nonwoven, or you can have biopolymeric fibers and natural fibers to produce a hybrid yarn. This hybrid yarn can also be used, as Fernando already said, to produce a hybrid fabric. However, you can also produce a hybrid fabric using a biopolymeric yarn mixed with a natural yarn, but directly in the structure during the weaving process. When the polymer is in a resin or liquid form, you can use an impregnation process where the resin formulation must have low viscosity to allow the immersion of the reinforcement structures. So this process starts with the impregnation of the textile structures in the resin that afterwards passes through a series of nip rollers to regulate the resin content and the prepreg thickness. Afterwards, the prepreg is dried to eliminate the solvent. Usually, this process is used for thermoset polymers, however, can also be used for thermoplastic polymers, and as the advantages of being able to be performed for diverse textile structures. However, during the drying stage with the solvent elimination, it can lead to high porosity of the prepreg structure. When the polymer is in liquid form, you can also do a spray or a knife coating. Regarding spray coating, it consists in applying a polymeric dispersion through airbrushes or spray guns, and it has the advantage of reducing water, chemicals, and energy consumption. Regarding the knife coating, it begins with the polymeric formulation, named as coating paste, that is applied on a textile substrate using a coat blade or a knife coater. In this case, the thickness of polymer layer is given by the distance between the knife coater and the textile substrate. Here we have a comparison between some of the methods that I already presented, and we can see that regarding melting impregnation, it has a excellent result regarding flow path and degree of the impregnation, having a moderate drapability. Solvent impregnation and film stacking have shown similar behavior, showing a moderate flow path and degree of impregnation, but both of the processes result in bad drapability. Regarding powder coating, it is the least effective method, leading to a low degree of impregnation. It doesn't have a good flow path and drapability. However, hybridization is shown as an effective and promising method for prepreg obtention, since it leads to a high degree of impregnation and it has drapability, which can help when we are forming the composite. So the advantages and the disadvantages of using prepregs on the composite production are the following. Regarding the advantages, is easy of use because the impregnation step has already been done. It leads to a low void content in the final composite. It imparts uniformity and repeatability to the composite and improves mechanical performance. The main disadvantage is the high costs, and in case of thermoset polymers, the storage and shelf life. So, as prepregs are intermediate structures to make composites, we can apply multiple layers of prepregs, and then through a thermocompression process, we can give form to these prepregs and produce a biocomposite. The main applications were already mentioned before, but are the automotive sector, both for interior components and structural parts, boats and navy, also for structural components and interiors, supports for multiple equipment and also structural parts of some equipment, and construction and furniture, for example, for wallpapers, luxury furniture, and facades. In the BIT project, we are working on some of the approaches that I explained before, namely hybrid nonwovens. We have a pilot line of needle punch nonwovens in CITEV, and we are mixing polyamide fibers with hemp fibers to produce hybrid nonwovens that afterwards are thermocompressed to produce biocomposites. Here we have an example of the use of the hybrid fabrics obtained from a biopolymeric yarn and a natural yarn directly mixed on the weaving process. And as you can see, the resulting textile has the drapability of a common textile, and it becomes stiff after the thermocompression process. Here it's also possible to see that the biopolymeric yarn melts after the thermocompression process, leaving only the natural yarn as the reinforcement structure. Here we have also a prepreg produced by a layer alternation method, and also the cross-section of this prepreg, where you can see the good impregnation of the polymeric film. This bioprepreg is 100% bio-based, made from polyamide and hemp. And with this bioprepreg, we already have made fully bio-based composites that are being used for our final prototype. That will be door panel, where our composite will be in the armrest as a structural component, and also we'll be using for the rest of the prototype coating textile with bioformulations also developed in BIT project. And I think that's all I have to say to you. I hope you enjoyed, and if you have some questions, feel free to ask me.
Thank you very much, everyone. So basically, we finished a little bit late, just 6 minutes late. So thank you very much for our speakers to make everything more or less on time. And I just put in the chat all the emails for you if you need to contact them, if you need some more information, and also mine if you have some doubts, issues, or anything related with the general training activities. So thank you very much, everyone, for being here today. And I hope to see you again in other training activities of this series. You can check on our website for the next ones. And thank you very much, everyone.
Thank you.
Thank you.
Bye-bye.